All right, let's get going. So we're talking more about exponential functions. We'll talk about logarithms today. We'll talk about kind of how they work as well. And as always, if there are things you specifically would like to see or have questions about, you're welcome to let me know in class or ahead of time or just ask a question. I'm really, really happy to kind of help you see whatever things you want to see about. And I didn't quite, I saw that Tav posted a homework assignment. I still haven't gotten access to Lee's Canvas, but I should email him again. Yeah, all right, well, let's take a look at these problems I've written here. So first off, we want to find the derivative of e to the x times tangent of x. That's definitely going to require a use of the product rule. When I'm doing the product rule, I'm always thinking about having just two pieces and doing kind of the derivative of one thing times the other and then switching it. So I'm going to have the derivative of e to the x times tangent of x plus e to the x times the derivative of tangent of x. And some people like to label these things. Some people might say like, this is your f, this is your g, there's your f prime, there's your g, there's your f, there's your g prime. If you like, totally unnecessary, but it's nice to see kind of what work we have done to get there. Welcome, come on in. Jamie, right? Yes. We're just getting started. So the derivative of e to the x is e to the x. Leave tangent alone. And then e to the x is e to the x. And then the derivative of tangent is secant squared of x. So there's our derivative of e to the x times tangent of x. Here's one that's a little bit more, well, not. Here's one that's going to require the use of the chain rule. We don't just have the derivative of e to the x. Now we have the derivative of e to the stuff. And as I said last time, I'm going to say it again because it's important. And I saw this in Tab's notes. He did it as e to the u, which is typical. But I'm going to write e to the stuff because that's what I like. The derivative of e to the stuff is just e to the stuff times the derivative of the stuff. That's it. That is how I would actually literally say it out loud and in my head, because that's what I say in my head. Like when I'm doing the derivative of e to the something, I'm like, oh yeah, we've got e to the stuff. The derivative is e to the stuff times the derivative of the stuff. So here that's going to be e to the stuff. So e to the x to the 7 plus cosine of x times the derivative of that stuff. Now, normally I would skip this step. Normally I wouldn't just write x to the 7 plus cosine of x prime. I would just be like, yeah, I know what the derivative of that is. That would be 7x to the 6th minus sine of x. But it's also perfectly fine and normal to write that intermediate step if you like to. So that's going to be times 7x to the 6th plus negative sign, but I would write minus sine of x. One thing that is important to note here is that you definitely need parentheses around all of this, because it's e to all this times each of these things. If you forget the parentheses there, it's actually wrong, because without the parentheses, you would just be multiplying the e to the x to the 7 plus cosine of x times the 7x to the 6th. And then after that multiplication, you would be subtracting off sine, which is not what we want to be doing. We want e to the stuff times the entire derivative of all that stuff. So make sure that chain rule part, that derivative, is always in parentheses. Sometimes it doesn't have to be because it's only one piece, but it's still fine to put parentheses around it. You can almost never go wrong by adding an extra parentheses. Almost, unless you're like doing weird things with parentheses. Okay. Let's look at one more. Let's look at, just to remind ourselves, and it's been a while. Let's say I want to find, let's write it, I'm going to write it differently. Instead of writing ddx of something, which means find the derivative of, let's write it as we have f of x equal to e to the x squared. That was interesting. Over x to the 4th plus, sure, sine of x. We want to find the derivative. And I would say generally, we shouldn't worry about simplifying our derivatives unless we have a good reason to. we're asked to, is a good reason. Or if we maybe need to set it equal to 0 to find some sort of critical point. Those are the usual reasons I'm simplifying a derivative. Other than that, not so much. So why don't you all give this one a shot? Try using the quotient rule. I'll remind you it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. I'll give you a minute and 15 seconds. Wow. You really gonna lose it on the one piece of paper I actually need. All right, well, it's been more time than I said it would be. All right, so let's take a look here. So whenever you're using the quotient rule, you can say this however you like. I like to say it's the bottom thing times the derivative of the top thing minus the top thing times the derivative of the bottom thing, all divided by the bottom thing squared. You might have learned like low d high minus high d low over low squared or whatever other mnemonic device you prefer. But I say lots of words in my brain. So then we actually have to find the derivatives of the things we have to take the derivative of. So we're going to get x to the fourth plus sine of x in parentheses times the derivative of e to the stuff is e to the stuff times the derivative of that stuff. Now, technically, I don't need to put parentheses around that because there isn't addition or subtraction to distribute to. I still feel better about it if I put parentheses around it. I just like to. Minus e to the x squared times the derivative of x to the fourth plus sine of x is going to be 4x cubed plus cosine of x, all divided by that denominator squared. So x to the fourth plus sine of x, quantity squared. And I wouldn't do another thing. I'll leave it at that. I'm really annoyed that I can't seem to find the notes that I knew I had in here earlier. Not you, where's your friends? Did I hide you? Annoying. All these good examples of things I'm gonna do. I mean, I can come up with stuff. It's just nice to have. Let me just make sure I didn't like magically spirit it away. Nope, not here, not here. Probably sitting on my desk. Give me one moment while I pretend to look for this thing and maybe make it magic. Maybe it's in here somewhere. Nope. Lame. Okay, well. What's that? Okay, what are you arguing about? Ah, I see. I mean, I think it's kind of great. Bagels are wonderful. Okay, so let's continue on. Let's talk. So we're definitely not done with exponential functions, right? We're gonna continue talking about, but let's spend some time talking about kind of their partner logarithmic functions. So logarithmic functions. And I don't know if what I'm about to say is 100% true, but it's true enough. Really, the reason we have logarithmic functions is because we wanted an inverse of the exponential function. So very much how, like, if you had the function, I don't know, say f of x equal to x cubed, where it takes an input and gives you some output that's the cube of it, the inverse function is the function that undoes that. It's f inverse of x, and it's equal to the cube root of x. Those two functions undo what the other one does. I always think about it as the input and the output reversing roles. Here, if I plug in, say, -2, f of -2 is -2 cubed, which is -8. Right, -2 times -2 times -2. And inversely, f inverse of -8 is the cube root of -8, which is indeed -2. So literally, these functions interchange the role of the input and the output, as do logarithmic functions when compared to their exponential brethren. So, for example, we talked a little bit last class about f of x equal to 2 to the x. We graphed it, we plotted some points. Actually, we did it in the reverse order. Right, and I'm just gonna remind you, look like this. And some nice points like the point 0, 1, and the point 1, 2, and the point 2, 4, and the point 3, 8. Not that those are all the points, they're just some of the nice ones to plot. So if I want to find the inverse function, there's actually a process, which I don't think we need to get too caught up in. But the process normally is you switch x and y, and then you try and solve for x or for y. So we could say we've got y equal to 2 to the x. We're going to switch x and y. So we'll switch x and y at the end. I like to switch them first. And then we try to solve for y. And the problem is there's not really a good way to solve for y without making up an entirely new function. So we're going to say, okay, well, the solution here is that we're going to say that x equal 2 to the y means the same thing as y equal to log base 2 of x. And I really have to emphasize strongly here. These two equations, they're not the same equation, but they have the same meaning. In both of these equations, plural, x is playing the same role and y is playing the same role. Y is the exponent, and x is the thing that 2 raised to that exponent happens to be equal to. So when I look at something like this, and actually I'm going to write down my favorite equation. I got lots of favorite equations, as you know, math people should have lots of favorite equations. One of my favorite equations is log base 2 of 8 is equal to 3. And when I look at that, what I'm really reading in my mind is 2 raised to what power is equal to 3? Oh, it's 8. Oh, I said the wrong words. 2 raised to what power is equal to 8? The answer is 3. Oof. When I look at this, I also kind of say, there's my base. It's raised to that power, and it's equal to that number. So just as another example, before we start graphing things here, if I wanted to find log base 5 of 25, I would be asking myself, 5 raised to what power is equal to 25? And the answer is not 5, because 5 times 5 is 25, but 5 to the 5th is much, much larger. The answer here is 2, because 5 to the 2nd power is equal to 25. And just for a couple more interesting examples, I want to say, like, find log base 4 of 1/16, I would be asking the question, 4 raised to what power is equal to 1/16? Well, I know 4 squared is 16, so I know that 4 to the negative second is equal to 1/16. Each of these logarithmic equations I've written have an exponential analog, right? I'm not writing it, but I'm about to though. This is the same as 2 to the third equals 8. This is the same as the equation 5 squared equals 25. This is the same as the equation 4 to the negative second equals 1/16. It's just a different way of writing the same information. Okay. I'll point out one more time. Actually, I'll point it out lots more times probably, to be honest. If you have f of x equal to 2 to the x versus, I'm gonna write the inverse as g of x equal to log base 2 of x. The inputs and the outputs changed places, which is literally right. When you're finding an inverse function, that's why you switch x and y, because you're changing the roles of the inputs and the outputs. Here, I am going to make a table with some values just for the fun of it. We have x values and we have 2 to the x, and I'm going to make my usual list of like 0, 1, 2, 3, -1, -2, -3. 2 to the 0th is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the -1 is 1/2, 2 to the -2 is 1/4, 2 to the -3 is 1/8. The reason I'm making this list is to make it easier to make the other list, to be actually honest about it. If I wanted to then plot x values and log base 2 of x values, I'm going to say the words that are mathy, but what I'm really doing is I'm taking every pair in this list and just flipping where they are. So instead of getting 0, 1, I'm going to get 1, 0. Instead of getting 1, 2, I'm going to get 2, 1, 4, 2, 8, 3, 1/2 -1, 1/4 -2, 1/8 -3. Because they're doing the same thing, right? If I ask, what's log base 2 of 4, this one's always tricky. It's not tricky because it's hard, it's tricky because it can lead you down the wrong thought process. Log base 2 of 4 is equal to 2. But it's because 2 squared is equal to 4, not because 2 times 2 is equal to 4, although it happens to be true as well. That's why it's a terrible example. A better example is log base 2 of 8 be equal to 3. 2 times 3 is 6. 2 raised to the third power is 8, which is the correct way of seeing what's happening here. And in lots of other ways, right? Log base 2 of 1/4 is equal to -2 because 2 to the -2 is equal to 1/4. So I'm kind of hitting this relatively hard, but that's the idea here. Let's look at the graphs of these two inverse functions. We'll try to draw them as nicely as possible. I'll say many more times, if you haven't already, please get comfortable using Desmos. It's just a good tool for exploring things. I'm super jealous of you all that you have that tool at your fingertips to use whenever you. I wish it had been. Actually, really, I wish I had the 3D graphing stuff when I was a student. Like the 2D graphing stuff, there were TI, whatever calculators, but like the 3D graphing was still not all there. It's really wonderful. So let's see, here's my graph of 2 to the x. Got my usual points, 0, 1, 1, 2, 2, 4, 3, 8. And then the stuff to the left, I just kind of pretend like I'm graphing it because it's hard to draw things so small. There's my f of x equal to 2 to the x. And now I'm literally taking every xy coordinate pair and interchanging the xy values. I get 1, 0, I get 2, 1, I get 4, 2, I get 8, 3, 3. It looks like that. And graphically, the interesting thing about inverse functions is that they are reflections of each other. They are reflections across the line y equal to x, which makes some sense if you think about the fact that we are interchanging the values of x and y. So these totally are reflections of each other across that line y equals x. Kind of cool. I think it's actually really cool. Right, that point goes to that point. That point goes to that point. If your drawing is better, the points look like they're really kind of going perpendicular. Right, but there's, you know, there's 8, 3, there's 3, 8. By the way, I try not to stop and say this, but do you have any questions? But really, anytime you have questions, you should just be asking them because you're always welcome to ask questions. Here's another cool thing about logarithms, or more generally, functions and their inverses. All the things that were true about the exponential function that we talked about last class. So let me remind you before we say all the other things. So last time we talked about how, and I'm gonna say, I'm gonna be a little bit more general here. If you have f of x equal to some b to the x, b is our base. Some books use b, some books use a. It doesn't really matter what letter people decide to use here. But I will point out that for exponential functions, our base needs to be greater than 0. And our base also needs to be not equal to 1. Greater than 0 because if you have the numbers that are less than 0 or equal to 0, well, 0 to any positive power is just 0. It's not very interesting. 0 to a negative power is actually undefined. Right? 0 to the negative 2 is like 1 over 0 squared, which is dividing by 0. And then negative numbers to weird powers become problematic. You might get things that are not real, like -4 to the 1/2 power is the square root of -4, which is imaginary. So that's why we limit ourselves to having bases that are nice, positive numbers. And then not 1, also because 1 is not interesting. 1 to any power is what? Right, so 1 to the x isn't really an exponential function. It's just a constant function. So for something like this, which again has this usual exponential shape, that's if b is larger than 1, because right, if it's less than 1, then it goes down from left to right. But we have all the things from last time. Our domain was all real numbers. Our range was all positive numbers. We have a horizontal asymptote at y equal to 0. We have a y-intercept at 0, 1. And although I don't really feel like I need to say it, I am going to say it. We have no vertical asymptote, and we have no x-intercept. And then it's continuous and differentiable, but that's not really what I'm getting at here. So, all right, now for the logarithmic function, what's going to be really kind of neat here is all the x and y things, are going to interchange because that's literally what we are doing. So if I wanted to say graph g of x equal to log base b of x, which again has this usual logarithmic shape. I could show you guys something cool in just a second. I mean, lots of cool things, but you know, the extra cool. So here, our domain is all positive numbers from 0 to infinity. Our range is all real numbers. The domain and the range have switched, which happens when you find an inverse function. We have a vertical asymptote at y, sorry, not at y, at x equals 0. And we have an x-intercept. Not at 0, 1, but at 1, 0. Here we have no horizontal asymptote. We have no y-intercept. So every x or y thing here has switched to the opposite x or y thing over here. Our domain, which is all x values, became our range. Our range, which is all y values, became our domain. Our horizontal asymptote, which was y equals 0, became a vertical asymptote at x equals 0. Our y-intercept at 0, 1 became an x-intercept at 1, 0. Our lack of a vertical asymptote here became a lack of a horizontal asymptote here. Our lack of an x-intercept here became a lack of a y-intercept here. So all of these things translate into their kind of opposite or inverse thing in the inverse function. All right. Let's see, what else to say about logarithms here? Sure, there's lots to say. Let's talk a little bit about, yeah, we should talk a little about some of the rules of logarithms, and then we will, yeah, I guess we do form graphs too. So let's look at a few more. I mean, I'm always like a few more things, just a few more things. It's always a few more things until the class is over. Sure, let's graph a few things. We've got some problems here. Oh yeah, so yeah, let's go here first. So a few things about logarithms. Oh, actually, I know what I was gonna say first of all is, so you all have younger hands than I do, but look at your right hand for a second. You might, on your right hand, be able to more easily see this nice kind of curve here and this nice kind of curve. I can't really, right there, kind of. I've always thought about how this looks like your exponential function, e to the x. This looks like your logarithmic function, natural log of x. So it's kind of a nice, like most of you are right-handed. So if you're taking a test, like look at your right hand, set down your pencil, look at your right hand. If you look at your left hand, you've got like e to the negative x and the natural log of negative x, which is not as useful, but still good. But yeah, if you're left-handed, you're set, right? You're like, yeah, I can look at my right hand without putting down my pencil. It's awesome. But a few other things about logarithmic functions. So first of all, we have some rules. So there's the product rule for logs. And we really should say for logs, because if someone says product rule, they mean like the derivative product rule. And this is that the log base b of x plus the log base b of y is equal to the log base b of the product of x times y. I like to see an example of each of these things just to make sure they really kind of make sense to me. So let's check it out. So for example, the log base 2 of 8 plus the log base 2 of 4. I want you all to find out what nice whole number that is equal to. I see some of you saying, yes, it is definitely log base 2 of 8, which is 3, plus log base 2 of 4, which is 2, which is 5. But that's not what the product rule is. We're going to use that to see the product rule. The product rule would tell us that this is equal to log base 2 of 8 times 4, which is log base 2 of 8 times 4 is 32. And 2 to what power equals 32? I'm pretty sure it's 5. 2 times 2 times 2 times 2 times 2 is 32. So yeah, that's equal to 5. So either way you slice it, whether it's log base 2 of 8 plus log base 2 of 4 or log base 2 of 8 times 4, you get the same value, which means they're equal to each other. Now, there's lots of other numbers where it's much harder to see it because things don't work out nicely. But just for one more example, it is also true that log base 6 of 4 plus log base 6 of 9 is equal to log base 6 of 4 times 9. Do I know what log base 6 of 4 is? Definitely not. It's some terrible irrational number. You could use a calculator to find it. I mean, we can use a calculator to get an approximation of it. I actually brought my good calculator to do that. I say before I actually check it. Yes, I actually brought my good calculator. And if I wanted to calculate log base 6 of 4, it would be, let's see, just for fun. Where are you here? It'd be about 1.292481225, and the list goes on. But check this out. When you add these together, you multiply the arguments. 4 times 9 is 36. And we can all find that log base 6 of 36 is how many? Yeah. That's kind of a neat thing you're able to do with these. There's also a quotient rule for logarithms. And it works very similarly. Instead of when you add, you end up multiplying the arguments. When you subtract two logarithms, log base b of x minus log base b of y,
you end up dividing their arguments. You get log base b of x divided by y. And then, I don't think, I feel like we don't really need an example for that, although I'm happy to provide one if we would like to see one. And then there's also a power rule for logarithms. And this is probably of all the three of these rules, although you've probably maybe seen all of them at one point, or used all of them at one point, the one I would imagine you're probably the most familiar with or have used the most is this one, where if you have log base b of x to some power, it's equal to that power times log base b of x. Or as we often say, the power comes down in front of the logarithm. This is, to me, this is really just an application of the product rule. If you have, just like how repeated addition is multiplication, it's kind of the same thing here. Repeated multiplication ends up just being exponentiation. So for example, if I had the log base 2 of 7 to the third power, I don't know what that is. No one should know what that is. I mean, maybe someone knows what it is because they're like, have a brain that works that way. But I can see that this is log base 2 of 7 times 7 times 7. And that's what 7 to the third means, 7 times 7 times 7. And then I could break this up using the product rule. I could say, oh, I've got the log base b of something times something. In fact, I could even do this in two parts. I could have 7 times 49 and break it up as the log base 2 of 7 plus the log base 2 of 7 times 7. And then I could break that up again. I don't really need to take 2 steps to do this, but it's perfectly fine. Say that's log base 2 of 7 plus log base 2 of 7 plus log base 2 of 7. But I'm adding up the same thing 1, 2, 3 times. And just like 5 plus 5 plus 5 is 3 times 5, log base 2 of 7 plus log base 2 of 7 plus log base 2 of 7 is 3 times log base 2 of 7. So that's why that rule works that way. The power just comes down. What else do we need to say about logarithms before we get into the real meat of things here? I need more paper. Good thing I have more paper. Yeah, let's say that. So a few notational things that everyone needs to be aware of. If I want to find the log base 10 of say 1,000, I'm not going to write it that way. Why? Because 10 is very common, right? We're kind of a base 10 society in a lot of ways, not all the ways, right? We're also base 60, base 12, right? All these other bases get used for time or calendars or whatever. But base 10 is a frequent base that gets used a lot. And so whenever I have base 10, I'm just going to not write it. I'm just going to write log, and everyone's going to know I mean base 10. Probably to save money on ink when they were typesetting things back in the day. They're like, oh, this 10 is coming up so often. Let's just not put it in there. And so, but that would equal 3, right? Because 10 to the third power is 10 times 10 times 10, which is 1,000. The other very common base that you should all get real comfortable with is the natural base. So log base e of some x. I don't want to write 4 letters because I'm lazy. A lot of math writing just comes from mathematicians being lazy. We're like, I don't want to write 4 things when I could write less things. So we're going to write this as the natural log of x. You are welcome to say ln instead of natural log. I will say natural log, literally because I used to have an office around the corner from a woman named Ellen. And I would be saying ln to my students. You'd be like, yes, can I help you? But no, I'm talking about logarithms. So I started saying natural log because that way she didn't get confused. But I will say natural log. It's just an abbreviation, right? When I say natural log of x, it really just means log base e of x. We're just not wanting to say and write all those things all the time. If I was trying to find the natural log of e to the third power, I'd be asking e to what power equals e to the third power? Seems like kind of a silly question. The answer is just 3. You could also take extra steps to get there.
You could say, oh, I'm going to bring the power down. That's 3 times the natural log of e, and the natural log of e is just 1. Lots of ways to solve problems. In fact, that kind of brings up a couple more things. So a few more things I want you to be aware of, kind of just log things that come up often that maybe no one has ever said to you before. The log base b of b is always going to be 1. B to what power equals b? B to the first power equals b. Similarly, log base b of 1. Again, assuming that b is a positive number that isn't 1 itself. B to what power equals 1? Use a real number. 5 to what power equals 1? Right? 5 to the 0th equals 1. 10 to the 0th equals 1. A million to the 0th equals 1. So whenever you take a log of 1, you end up getting 0. Again, these have their exponential equation equivalents, right? This is literally meaning the same thing as b to the first equals b. This means the same thing as b to the 0 equals 1. And then even though this is very general, I might also write them down for very specific cases, like, for example, the log of 10 is equal to 1. The natural log of e is equal to 1. The log of 1 is equal to 0. The natural log of 1 is equal to 0. I'm really just writing down special cases of these two things I've already written up there. Okay. The last thing I think I want you to know about as far as logs are concerned before we kind of get moved towards talking about the derivative of logarithmic functions is the change of base formula. So sometimes you might encounter a calculator if you're trying to like approximate a logarithm that doesn't have, most calculators have, it depends. Most calculators used to not have a button that was like log base whatever you want. Like if I wanted to find, in fact, if I wanted to find, what was I finding before, like log base? I don't know. I was finding something interesting before just a second ago. I was finding log base 6 of 4. If I wanted to find log base 6 of 4, I didn't type that into my calculator because I don't have a log pick your base button in my calculator, at least, or it's not easy to find if I have one. Instead, what I actually typed in my calculator was the natural log of 4 divided by the natural log of 6. Because those are equal to each other. And let me show you how we get there, because I think it's in fact, it's not only is it a worthwhile process, it's a process you're going to use kind of to help you find derivatives of other things in a little bit. So here's what I did. I said log base 6 of 4 is equal to some number. I'm going to call it x because x is typical. And now let's rewrite this as an exponential equation. So let me ask everybody, people on Zoom too, you can think about the answer. What's my base? Is it 6? Is it 4? Or is it x? It's definitely 6. The base is always the thing that's lower looking, right? That's why like the base is like, just like the bass, like in music, the bass is low. The base is the low thing. My base is 6. What's the exponent or the power? Is it x or is it 4? It is x, yeah. Just like, right, just like in the previous pages, right? That's not a good page. Yeah, sure. Fine. Right, just like here, when log base 2 of 8 was equal to 3, 2 was the base and 3 was the power. 8 was the thing it was ending up equal to. So the thing that you actually hear people say this, people will say a logarithm is an exponent because the logarithm is the exponent that you need to get from 6 to 4. So 6 to the x is equal to, the only thing left is the 4. And then we're going to take the natural log, or really any logarithm base you like. I just like the natural log because it's less writing. But we'll write the general formula in a second here. I'm going to take the natural log of both sides. The natural log of 6 to the x is equal to the natural log of 4. Okay.
Now we're going to use the power rule and bring the x down in front. So we're going to say that x times the natural log of 6 is equal to the natural log of 4. And then finally, divide both sides of this equation by the natural log of 6 to isolate x. You end up getting x equal to the natural log of 4 divided by the natural log of 6. So here's why there's a lot of reasons I like the change of base formula. It's another great formula. Here's one example. Maybe I want to find what log base 4 of 8 is. I'm like, that shouldn't be that hard. It's not 2, right? Because 4 squared is 16. It's not 1 because 4 to the first is 8 oh my God. What did I just say? 4 to the first is, I tried to stop myself before I said 4 to the first is 4. But it's something between 1 and 2. Because there should be some power between 1 and 2, so the 4 to that power is equal to 8. What do I know about 4 and 8? Well, that's a terrible question. Let me ask a better question. What base do 4 and 8 have in common? What are 4 and 8 both powers of? Right, 4 is 2 squared, 8 is 2 cubed. So let's rewrite this using a change of base formula. Instead of natural log of 8 over natural log of 4, let's use the common base. Let's say that's equal to log base 2 of 8 divided by log base 2 of 4. Totally valid, totally correct. We know what log base 2 of 8 is. It's 3. We know what log base 2 of 4 is. It's 2. And it is certainly true that log base 4 of 8 is equal to 3/2. It's kind of great. There are other ways of solving this, right? The other way of solving this would be to say something like log base 4 of 8 equals x. Rewrite it as 4 to the x equals 8. Rewrite 4 and 8 as powers of 2. So you have like 2 squared to the x equals 2 to the third. And then rewrite the left-hand side as 2 to the 2x equal to 2 to the third. And then if the bases are the same, the powers have to be the same. So 2x is equal to 3, which means x is equal to 3 divided by 2. Oh, look, we got the same answer. I think it was easier to do it the first way, but I feel like the first way you have to the first way requires a little bit more like slickness, right? Like it might not be super obvious that you could do that right off the bat. Okay, let's write down the general change of base formula, and then I think we'll get into, we'll get into it. I mean, we're already in it, right? Okay, so change of base formula. I would say that there are kind of 3 normal versions of this. So if I want to rewrite the log base b of x, I would almost always rewrite it as the natural log of x divided by the natural log of b. Notice, conveniently, I think, the thing that looks like it's lower, the b, ends up in the denominator. And the thing that looks like it's higher, the x, ends up in the numerator. And that's always true for the change of base formula. But really, you don't have to pick your base being e, the natural base. You could pick base 10 if you want. Or you could actually pick any base you like. Log base a of x divided by log base a of x. B of b. Goodness gracious. All of those are equivalent to each other. It's kind of great. Let me show you why. For the same sort of reason. So let's say I wanted to start with the log base b of x. I better not say it's equal to x, because I've already used x. Let's pick any other letter in the alphabet. I would probably pick y if I've already used x. But really, you can choose whatever you like. Let's rewrite it. B raised to the y power equals x. And now pick your favorite logarithm. Log base a, log base e, log base 10. I'm going to go very general and say log base a. And take the log base a of both sides. I really want to emphasize here, a logarithm is a function. You are taking the log of an argument. We are not multiplying by log base a. We are taking the log, just like you take the square root of both sides of an equation, or square both sides of an equation, right? You're not multiplying both sides by a square root. You are taking the square root of the argument. So log base a of b to the y
equals log base A of X. Use the power rule, bring down the Y. In fact, I almost always like you could come down there. And then we have Y times log base A of B equal to log base A of X. And finally, divide both sides by log base A of B to get log base A of X divided by log base A of B. So log base B of X is equal to log base A of X divided by log base A of B. And that A could be base 10, could be base E, could be base 2, could be base 7, any positive number that you like except for 1. Quick aside, I will point out that even though a base can be any positive number, you normally only see bases that are positive integers, like 2, 3, 4, 5, etc., or E. Technically, you could have a base of 1/2, though, or a base of 2/3, or some other fractional number that would be kind of strange. Okay, let me grab. Where'd you go? Really, I can't just keep there. Hide it over here. Cool. Much like the exponential functions, when I'm graphing the logarithmic functions, I'm not trying to plot a whole bunch of points. So, for example, if I were asked to graph, say, y equal to log base 3 of x. Yeah, just that. I wouldn't do anything other than draw my vertical asymptote at I wouldn't even draw a vertical asymptote because it's the y-axis. But I would just draw the intercept, and that's kind of all she wrote. My intercepts, I'm not going to plot my intercept. I'm just going to try drawing the thing in the usual shape. And then saying, oh, that's got to be the point 1, 0. This should look like it gets larger and larger and larger forever and ever and ever. It just slows down. It doesn't quite flatten out. Like it kind of looks like it maybe should flatten out, but it doesn't. It does get infinitely large. It just would take a really long time. I mean, so would anything, I guess, but logarithms take longer than other things. Let's graph a couple more. Let's do that. Yeah. Let's graph g of x equal to log base 8 of x plus 2. All right. Which way are we shifting? Left or right? I'll remind you, when it's horizontal, it's kind of counterintuitive. Yeah, it's left. Now, actually, this one I feel like is easier to figure out if we think about the domain. So I'll remind you all, for logarithmic functions, the argument has to be positive. So here, our domain, we have to have the argument x is greater than 0. Which we have, right? We were just to the right of x equals 0, which is the y-axis. Here's x equals 0, our vertical asymptote, our y-axis, and we're to the right of it. Here, same thing is true, the same thing meaning that the argument of our logarithm, in this case x plus 2, has to be greater than 0. And that's going to boil down to x having to be larger than -2. So our vertical asymptote here is going to be at x equals -2. I always think about the vertical asymptote for a logarithm occurring where you would have a 0 input. So if x is -2, -2 plus 2 is 0, and the log of 0 gives you a vertical asymptote. Interesting fact, I think logarithms are kind of the only functions that have vertical asymptotes where you're not just getting it by dividing by 0. Right? Every other kind of function where you encounter a vertical asymptote, it's because there's some sort of fraction or rational thing, and the denominator is getting closer and closer to 0. The logarithm is kind of the one exception, which I just think is interesting. So here, I'm going to go left 2. So there's my new vertical asymptote. X equals -2. And then I'm going to graph this thing. I could either
Note that the x-intercept is going to be -1 because it's just my previous x-intercept shifted 2 to the left. If I don't like that, I could find the x-intercept by setting y equal to 0. So set the whole thing equal to 0. Rewrite it as 8 to the 0 equals x plus 2. 8 to the 0 is 1. 1 minus 2 is -1. So yeah, my x-intercept is negative. Oh, and I have a y-intercept as well. So we have to figure out what that is. Y-intercept is almost easier in my opinion. The y-intercept, we're going to set x equal to 0. We're going to get y equal to the log base 8 of 0 plus 2, which is the log base 8 of 2. All right. We know that log base 2 of 8 is 3. It's 2 to the third equals 8. What's log base 8 of 2? 8 to what power equals 2? Good question. Kind of like 3. It's 1 over 3. Yeah. 8 to the 1/3 power, or the cube root of 8 is equal to 2. So this is totally 1/3 because 8 to the 1/3 is equal to 2. If you really wanted to, oh, in fact, this is a totally cool place where you could also have used the change of base formula. You could have said, oh, 8 and 2 both have a common base of 2. So you definitely could. I was kind of thinking about, I was like, yeah, no, it totally works. You could totally have rewritten this as log base 2 of the top thing over log base 2 of the bottom thing. Everybody. What's log base 2 of 2? 1. What's log base 2 of 8 for the 20th time? Still 3. Oh, we got 1/3. So either way you slice it, that y-intercept is going to be 1/3. Cool. Okay. Almost there. I want to get to logarithmic derivatives today. I just feel like there's a lot of things about logarithms we should say to make sure we've I mean, technically you're supposed to have like seen them before in pre-calculus, but even if you did, that was a while ago. Who remembers all that? Few more things I want to say about logarithms, and then I think I'm ready to mention what the derivative of a logarithm might be. Okay. We talked about how logarithms and exponential functions are inverse functions. A lot, actually, today. So I'll just point out f of x equal to 2 to the x, and f inverse of x equal to log base 2 of x are, as the notation would imply, inverse functions. And really, you could do that for any base, right? It doesn't have to be 2. It could be 3 to the x and log base 3 of x. It could be e to the x and the natural log of x. It could be 10 to the x and log base 10 of x, which I'm just going to write as log of x. All of these are inverse pairs, inverse functions. What makes an inverse an inverse? Well, I would say it's the undoing. It's the fact that one of these functions exactly undoes what the other function does. So what that really means is that their composition gets you back to where you started. Let me show you what I mean. Let's say specifically for f of x equal to, what do I want here? Yeah, fine, I'll use 2 to the x. And g of x equal to log base 2 of x. Yeah, I know I changed the name because I didn't want to write f inverse. So here's what I mean. F of, let's pick something different. F of 5 is 2 to the 5th, which is 32. And then g, okay, watch this. I'm not going to write g of 32 first. I'm going to write g of f of 5. But f of 5 is 32. G of 32 is log base 2 of 32, which is 5. So the whole point here is that we started with 5, f did something to 5, and g undid whatever f did to get us back to 5. And more generally, inverse functions do this for any input value.
So what makes f of x and g of x inverses is because f of g of x is equal to x, and g of f of x is also equal to x.
No matter where you start, if you do one of them and then you do the other one, you'll get back to where you started. As long as you start somewhere that's in the domain, right? You can't start somewhere that's like not in the domain. That would be weird.
So what that means is that f of g of x, which is f of log base 2 of x, which is 2 raised to the log base 2 of x, is always equal to x.
And I really, really, really would prefer, although I can't make you do anything, but I would prefer that you don't say that they cancel. Because it's not so much that they cancel, it's that they undo each other. Here's how I would actually phrase it in my head. Log base 2 of x. In fact, let's use some real numbers here for a second. Let's say log 2 to the log base 2. Okay, I'll pick the easy one first. What's log base 2 of 8 for the 21st time? 3. Or as I might think of it, it's the power that I raised 2 to get 8. Okay, what's 2 to that power? What's 2 to the power that I raised 2 to get 8? Too many 2's, but right. This is the number that if I make that the power of 2, I get 8. And I made it the power of 2, so I better get 8. And it's easy to see when we know that log base 2 of 8 is 3 and 2 cubed is 8. But it also should work if you got a funky number. 2 to the log base 2 of 7 should be 7 because log base 2 of 7 is the number that you write as the exponent of 2 to get 7. And then we made it the exponent of 2. So we should get 7 because it's doing the thing we said it should do. So the whole point here is just that these functions undo each other. So more generally, b to the log base b of x is always going to equal x. And vice versa. Log base b of b to the x is always going to equal x. And then the version that I would actually write down or say in my head is that e to the natural log of x is always going to equal x, and the natural log of e to the x is always going to equal x. Those things always undo each other. The natural log of x and e to the x are inverse functions, so they undo each other. And we use these facts a lot. In fact, a lot of the time we start with something like x, and then for reasons, we rewrite it as e to the natural log of x to be able to do some stuff to it. All right, cool. Yeah. Okay. Yeah, we got time. So let's start off with some easy ones. Well, easy, but not. I want everybody to tell me what's the derivative of e cubed? Let me ask you a different question that might jog your memory. What's the derivative of 5? Close. 0, right? Because if you think about graphing y equal to 5, it's a horizontal line. Like that. And what's the slope of that line? 0. Right? Functions that are constants, right? That always have the same y value no matter where you are. They always have a slope of 0, and their derivative is 0. E to the third. Is that ever changing? Let me check. I'm putting my calculator here. See, where's my E button? I can never find it. E to the third is 20.08. Let me do it again and see if I get it. No, I'm not going to do it again and see if I get a different thing. We know that E to the third is always going to be approximately 20. But the point there is that's a constant. How do I know it's a constant without like plugging into a calculator? There's no X's. There's no variables there. I know E kind of likes to like moonlight or pretend like it's a variable because it kind of looks, but it's not. It's a number. It'd be the same as like if I asked, what's the derivative of 6 squared? It's no different. The derivative of e cubed is 0. The derivative of 6 squared, the derivative of 36 is 0. They're both constants. Their derivatives are both 0. And in the same sort of way, even funkier, the derivative of the natural log of 5. Do you see an x? I don't see an x. I mean, I see an x right there. That's saying take the derivative with respect to the variable x. Oh, there's no variables there. There's no variables. That means you have a constant, and the derivative of a constant is 0. I'm bringing this up now because it's gonna play a role in what we do in the future. So that's most of the time, I think I said this last time, I'm saying it again. Most of the time I don't just do things for the heck of it. Occasionally I will because I think it's cool. But in fact, I'll wait till the end of the month. So let's talk about the derivative of the natural log. So I want to find the derivative of the natural log of x. And this is kind of maybe, I think, really the last function we learn about how to take the derivative. And then you kind of have learned all the derivatives you'll ever need to know for calculus. There's a couple ways to do this. I think I'm going to do it. Yeah, I'm going to do it that way. So I'm going to do it this way. Let's say we're going to set y equal to e to the x. Usually people do this one of two ways. They either give you the derivative of the natural log and they derive the derivative of e to the x from it, or vice versa. So since we already learned about the derivative of e to the x, we're going to derive the derivative of the natural log from it. So why did I set y equal to e to the x? I'm getting ahead of myself. I apologize. I don't want to take the derivative of e to the x. I know that already. I want to take the derivative of the natural log of x. So we're going to set y equal to the natural log of x. Sorry about that. Sometimes my brain gets on to the next step before I've written down the previous step. All right, I want you all to rewrite this as an exponential equation. And let me just ask everybody, what's our base? E. Okay, great. Our base is E. You know the power, and then it should be equal to whatever's left over. So e to the something equals something. I'll give you like 10 seconds. Hopefully everybody on Zoom is also doing the things. I'm sure you are. Okay, so my base is E, my power is Y, and it's equal to X. And now we're going to take the derivative of both sides. And I'm going to remind you, I don't even need to remind you, actually. I'm going to point out that Y is a function of X. Right? It's not just X. It's something that depends on X. In fact, sure. So actually, before I'm going to step away from this for just 1 second. I'm going to ask everybody. I know we already did a couple of these in the beginning. But let's just do one more. What's the derivative of e to the x cubed plus 1? You all do that one. I'll give you 20 seconds. Almost out of water. Okay, that's about 20 seconds. All right, the derivative of e to the stuff is e to the stuff. What do I have to multiply by? Which is what in this case? 3x squared. Right? The power is always 1 less than the previous power. I know that I feel like we do x squared too often. Right? We do the derivative of x squared, which is 2x. And we're like, oh, there's just like the 2 comes down and it's just x, but it's really 2x to the first, right? Because it's 1 less. So the point here is that the derivative of e to the stuff, once again, as always, was e to the stuff times the derivative of the stuff. Okay, that's going to apply here as well. We're going to differentiate both sides. And the derivative of e to the stuff, check this out. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. On the right-hand side, the derivative of x is just 1. This is an example of implicit differentiation. right? Way back in, last quarter when you're doing implicit differentiation, you had like a bunch of y's, and whenever you, like, if you take the derivative of y to the fourth, you would get 4y cubed times y prime. You have to multiply by the derivative of the insides. Okay, let's solve for y prime. So y prime is going to equal 1 over e to the y. But somewhere on this page, I have written down that e to the y is equal to a thing. What is e to the y equal to? X. So it's really the case that y prime is equal to 1 over x. Or in other words, the derivative of y equal to natural log of x is y prime equal to 1 over x. So the derivative of the natural log of x is 1 over x. Cool. And then as soon as you learn the new rule for differentiation, you should automatically then expand it to the chain rule version or generality of that rule. So the derivative of the natural log of x is 1 over x. And you know me, I'm going to say the derivative of the natural log of some stuff is 1 over the stuff. And then what do I have to multiply by? Every time? The derivative of the stuff. Every time. A lot of people do write this as the stuff prime on top of the fraction as opposed to out. I really like to emphasize the nature of you're doing one thing and then at the end you're multiplying by the derivative of that thing, of the inside stuff. But it's perfectly fine to write the other way. So you might also write this as the derivative of the natural log of some stuff is equal to the derivative of the stuff divided by the stuff. Either way, totally fine. It's certainly nicer to write it this way when you're like trying to save space. So, oh yeah, what time is it? Okay. We end at 10 till, right? Yeah. Okay. So, what's the derivative of the natural log of x to the fourth plus 2x minus 7? Well, the rules apply. It's going to be 1 over all that stuff times the derivative of all that stuff, which in this case is 4x cubed plus 2. Minus 0 if you want to think about the fact that the derivative of 7 is 0. Which, yes, I would probably recommend writing it as 4x cubed plus 2 divided by x to the fourth plus 2x minus 7. But if I had already written this and didn't have to simplify it, I'd probably just leave it like that. Okay. Let's see. Why don't you all try this one? Find the derivative of the natural log of, sure, x to the 6th plus cotangent of x. Yep, trig's not going away. Still there. Never went away. You know where to start. Write it down. 1 over times. In case for the folks at home, if you haven't already gotten the attendance form, here's a link to it again. All right, a few more moments here. Let's see, we're gonna get 1 over our stuff. One thing I would say about the chain rule that always kind of happens is, pardon me, the inside of the function should always show up as is. Sometimes people accidentally like, well, I'll give you an example in a second, actually. And then we need to multiply by the derivative of that, which is, well, what's the derivative of x to the 6th? Yeah, 6x to the 5th. And then the derivative of cotangent. Anybody? Let me ask you a different question. Do you remember the derivative of tangent? Secant squared. Okay, so take your tangent and your secant squared and put a co in front of each of them. So now instead of tangent and secant squared, you have well, yeah, you have cotangent whose derivative is cosecant, right? Except there is there's a negative because co-functions, cosine, cotangent, cosecant, always have a negative derivative. Always. Cotangent, cosecant, and cosine, their derivatives are always negative. Cotangent is negative cosecant squared of x. Derivative cosine is negative sine. The derivative cosecant is negative cosecant of x times cotangent of x. So yeah, all the co-functions have negative derivatives. All the other ones don't. Oh, what I was gonna say is just chain rule stuff. Be careful, right? If I was gonna take the derivative of, say, cosine of x to the fifth plus 4x, I've seen people incorrect. I don't even want to write it down. I'll just say it the wrong way. I'll write it down the right way. I see people say that the derivative is like negative sine of 5x to the fourth plus 4, where they've done the derivative of the inside as the inside. The insides, people, I've heard students say something kind of clever, like cosine is like the guardian of this. You can't change that if the cosine or some of the functions out in front of it. So this cosine is guarding it. It's going to change in the negative sign, but it's still protecting what's inside of it. And then outside, you can take the derivative of that. Oh yeah, it's 5x to the fourth plus 4. But the argument of a function kind of always has to stay as the argument of the function. And then on the outside of that function, you can multiply by the derivative of whatever that inside argument was. Let's see. Oh yeah, we got all that things to talk about too. Cool. Oh yeah, oh man, there's so many good things to talk about here. Just yeah, let's look at something that looks wild. The derivative of the natural log of, sure, let's get crazy, x to the fourth times the square root of x squared plus 1 over sine of x times x minus 3 to the 6th power. Oh, that looks terrible. You will most likely see something akin to this on your first exam. And some people, not you all, because you will know better, but some people will do this the hardest way imaginable. They will say, oh, I've got natural log of some stuff. And they'll say the derivative, not incorrectly, is 1 over all that stuff times the derivative of all that stuff. And then take the derivative of all that. They're going to use the quotient rule and the product rule twice and the chain rule a couple times. And the point of this problem is to not do any of that. The point of this problem is to first use our rules of logarithms to expand this into many simpler things. And then after we have expanded it as much as possible, then to differentiate it. So here's what I mean. We're going to rewrite this first as, notice I'm still going to write this ddx symbol here, which just means take the derivative eventually, because I'm not taking the derivative yet. I'm just simplifying it, which means I still have to write the instruction that says to do the thing I'm going to do. So it's the derivative of the natural log of the top, x to the fourth times. Also, I would change any roots to powers. So instead of writing the square root of x squared plus 1, I would write x squared plus 1 the 1/2 minus the natural log of the bottom part. Sine of x times x minus 3 to the 6th. And then I see I have some natural logs of products. I'm going to break those up as well. So I have still the derivative of the natural log of x to the fourth plus the natural log of x squared plus 1/2 to, sorry, plus 1 to the 1/2 minus the natural log of sine of x. Now here's where I have to be a little bit careful. I'm going to write it the long way. Minus all of the natural log of sine of x plus the natural log of x minus 3 to the 6th. What I really want you to see in this next step is that this minus sign distributes each of those terms, and I get minus the natural log of sine of x minus the natural log of x minus 3 to the 6th. Or as I like to say, and I'm going to write an extra step here, even though I normally wouldn't. I got the natural log of x to the fourth plus the natural log of x squared plus 1 to the 1/2 minus the natural log of sine of x minus the natural log of x minus 3 to the 6th. All the factors that were in the numerator, the x to the fourth and the square root of x squared plus 1, are in logarithms with positive leading coefficients here. All the things in the denominator, the sine of x and the x minus 3 to the 6th, are in logarithms that are preceded by a minus sign. So all the things in the top end up having pluses, all the things at the bottom end up having minuses. Easy enough. So really, if it were me and I was trying to do this as fast as possible on the test, I would probably skip straight from this first step down to this step here. And then after that, I should still do one more simplification. I should bring down all the powers I can. I don't want to say my derivative of natural log of x to the fourth is 1 over x to the fourth times 4x cubed. I want to say I'm going to do the derivative of 4 times natural log of x, which is much easier. So do one more simplification. Still the, I forgot an equal sign here. The derivative of 4 times natural log of x plus 1/2 times the natural log of x squared plus 1 minus the natural log of sine of x minus 6 times the natural log of x minus 3. There's nothing to be done with x squared plus 1. You can't simplify that any further. You can't bring down the power because it's not the power on the entire thing. So now we finally get to actually take the derivative here. So notice I'm not going to write the d dx symbol anymore because I'm taking the derivative. I'm doing the thing it's telling me to do. The derivative of the natural log of x is 1 over x plus 1/2 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So 1 over x squared plus 1 times 2x to the first minus the derivative of the natural log of sine of x is 1 over sine of x times the derivative of sine of x, which is cosine of x, minus 6 times the derivative of the natural log of 1 over x minus 3. Sorry, the derivative of the natural log of x minus 3 is 1 over x minus 3. I know I haven't said it explicitly, but I will point out that for each of these functions that were multiplied by a constant, the constant multiple is just hanging out in front, right? The derivative of 4 times a function is 4 times the derivative of the function. The derivative of 1/2 times the function is 1/2 times the derivative, and so on and so on. I probably wouldn't simplify this, but I could. I can simplify this as 4 over x. The 2 here and the 2 here cancel to leave me with an x over x squared plus 1. Cosine divided by sine is cotangent. And I could write this as 6 over x minus 3. Again, not really a necessary step. But I will say, if you're maybe doing this problem from a textbook and you look in the back of the answers are probably going to look like that, not like that. So that's maybe a good plug for occasionally it's worthwhile to simplify because you might want to see what the actual book answers look like versus what your answers look like. And I guess it's time to stop. What time is it? My watch says it's time. It's 11:51. All right. So good stuff. We'll continue on Tuesday, I imagine. So, right, this is always the issue with Tuesday, Thursday is that you'll have Friday class. Oh, you won't have Monday class this week, right? Because it's a holiday. But usually on Thursday, then you would have 2 classes before you saw me again. So on Thursdays, I'm going to try to kind of push ahead of where you might already be so that you have some of that to carry you through Friday and Monday, and then we'll pick back up where things are on Tuesday. Reminder, I think the reflection is still open. The first reflection is still open for today, but I think it closes today at like 4. So if you haven't already done it, you should do it. It's super easy to do. It's like a few questions about things that are not mathy. And then the other one will open, I think, today or tomorrow. Please do it over the weekend. Let me know how the first week went in your actual class. Tell me what you want to see next week, and we'll carry on. All right. Have a lovely 3-day weekend.